Peace. Huh. Peace. Power. Mad liberator, death operator, rock the data, amazing flavor. Yo, the way I feel, sometimes it's too hard to sit still. Things are so passionate, times are so real. Sometimes I try to chill, mellow down, blow a smoke. A smile on my face, but it's really no joke. You feel it in the street that people breathe without hope. They going through the motion, they dimming down the focus. The focus get cleared and the light turns sharp and the eyes grow teary, the mind grow weary. I speak it so clearly, sometimes y'all don't hear me. I push it past the bass note, nations got to feel me. Then my love so hard that I'm hardly asleep. My flow forever deep in all the scriptures when I leave on a beat. My presence speak volume before I say a word. I'm beware, penthouse, pain the herb. Pray to the gates of the Jewish self, universal life. Like you know it well. I don't want to put on this vital force. Hollow writer, cause I ain't just swing on ramp, bring down time. Chop more, dying outside it. So they just be frightened. The suckers trying to hide like the struggle won't find it. And the jump up to the cloud, they clearly remind us everywhere. Penthouse, pavement, the curb. Cradle to the grave, talk up each of a shell. Universal ghetto life, holla black, you know it well what it is. You know, they know what it is. We know that it, there it is. Huh, what it is. You know, we know what it is. They know, y'all know what it is. You know, here it is. What it is. You know, we know what it is. They know, y'all know what it is. You know, here it is. Peace, power. Fantastic. Original. And always on time. And rocking your mind. It's like
Sit and come relax, riddle of the Mac, it's the patch. I'm a soldier in the middle of Iraq. What say about noonish, coming out the whip and looking at me curious, a young Iraqi kid. Carrying laundry, what's wrong, G? Hungry?
No, give me my oil, get out my country.
And in Arabian, barking other stuff till his moms come grab him and they walk off in a rush. Distrust, feeling like I was pissed up on wound. I'm like, surely hope that we can fix our differences soon. Buying apples, hun breaking on.
Brute, you take everything, why not just take the damn fruit like pasta?
I don't understand it. On another planet? 15 months of this stuff, how I'm gonna manage? And increasing this sentiment, gentlemen getting down on their Middle Eastern instruments. Realized trapping this crowd. Walk over, kicked one of my fabulous raps. Arab jaw drop, they well wish, they glad rap. Now the kid considered like an Elvis of Baghdad.
هذه ما تربحش وهذه ما تربحش، هذه ما تربحش، هذه تربح، هذه تربح، لازم، هذه ما تربحش وهذه ما تربحش دايما على لازم.
what it is.
إيه قاعد عند الفلوس وتشوف واحد يضحك واحد يبكي.
تو اللي بعتوك.
إيه أنا اللي بعتوني. ها.
What it is. You know, they know what it is. We know, y'all know what it is. Ecstatic, there it is. Huh, what it is. You know, we know what it is. They know, y'all know what it is. You know, here it is. What it is. You know, we know what it is. They know, y'all know what it is. You know, here it is.
Testing. All right, there we go. I think we're back up now. All right. Thank you for posting there and letting me know about the audio issue. 20 seconds ago, 40 seconds ago. But unfortunately, we're on kind of a 10-second delay here, so hopefully you can hear that now. I'll go over this again here just to let you know what was going on. These were basically free points. Again, if you're answering this in a real question here, keep it in mathematical forms. 82, choose 10, 24 factorial, right? How many subsets of size 10 are there from a set of size 82? How many permutations are there of 24 objects? Okay. Good now. Great. Thanks. All right. So back to our the second question here. Again, those are just freebie points. So what we're going to do is we have to test whether or not a graph is a complete graph. And it could have different efficiencies depending on whether or not it is represented by an adjacency list or an adjacency matrix, right? So let's go ahead and, well, first of all, here's the smart aleck answer, right? All you need to do is say if the size of the edge set is equal to n choose 2, where n is the size of the vertex set, choose 2, then output true. Otherwise, output false. Right? And yeah, you're using pseudocode there to get away with less work, but that doesn't give it sufficient details that the question is asking for. The question is asking for what happens when it's represented by an adjacency matrix for the first one. So here we're going to actually have to do some work on this. So here's our input. The input would be a graph represented by an n by n adjacency matrix, right? And whether or not it is symmetric, you know, the transpose is equal to the is equal to the matrix M. We'll go ahead and take care of that in our pseudocode, and we'll output true if G, graph G, is complete, false otherwise. Okay. That's nice ink, but it's kind of fat. All right, well, we'll just go ahead and here, let's go ahead and switch over to blue. This was being nice to us the other day. All right, so this adjacency matrix, you can say entries. I'll just go ahead and put on here that entries are going to be accessible with m sub ij, right? You could call it g sub ij if you want, since it's a graph or something. It doesn't really matter. All I'm going to do is for I running from, and we'll go ahead and use one indexing here, 1 up to n, right? For j running from, and we don't have to start on the diagonal at all, so we can go from I plus 1 up to, and then we also don't have to start all the way, we don't have to go all the way here, I guess. There, one less, up to n. And I will put in if the ijth entry is 0, so if m sub ij and is false, let's see, and m sub ji, this is where we're taking care of the transpose. We're checking, is I connected to j or is j connected to I, right? But if they're both 0, then that edge is missing. I can stop immediately and output false, right? Otherwise, at the end here, if they're all 1s, then output true. Right? And this level of detail was necessary for this particular question because we're saying that it is represented as a matrix, right? If you wanted to keep this in general, if you with graph algorithms, you don't have to worry about such a level of details. But this question was probing for knowledge for this. All we have to do for the analysis is, we're this check right here. So 1, our input is the matrix M. 2, our input size. Here you have to be careful. What's the input size of an n by n matrix? Well, you could say that it's n and then proceed from there, and that's fine. But I'm going to go ahead and say that it's n squared, right? Because it is an n by n matrix. Okay. So clearly this is probably going to be linear because we're going over all entries here. And we also have the assumption here that we can access the ijth entry or the jith entry here in constant time using random access, and that's fine too. 3, the elementary operation is going to be the either the equality test here, or this one here, or combine them, or just say 1, 2, 3, 4, 5. The edge check on line 3. Right. 4, how many times is that executed with respect to the input size? Summation of j running from I plus 1 up to n. Summation I running from 1 up to n minus 1, and you do it once. Right? And then you can solve for that, and you will eventually come up with that this is equal to something where it's going to be equal to n squared minus n over 2. Right? And if you want me to show you the details of that, I can. But otherwise, it's just solving a summation here using Gauss's formula, etc. And so obviously this is going to be order n squared, but remember that your input size here is this. This is equal to, if I replace this with n, that's my real input size, then this is order n, i.e. linear. Right? Okay. What does it look like? How does it look different? Or maybe it doesn't look different. It really depends on your analysis here. It might end up being the same because it's all going to depend on what we identify as our elementary operation for B. For B, we'll have the same input except for G represented by an adjacency list. And hopefully you remember an adjacency list. That's exactly what your homework input was, that you have a vertex V sub I, and that's a linked list or some kind of a list where it links to a set or a list or something like that of the vertices that it is connected to. Right? And likewise, A has a list and V may or may not be in that. You have to maybe check both of those things. So what I need to do is I need to make sure that, now there are lots of ways that you could do this and lots of ways that you could come out with a different answer. It all depends on that 5-step process, what you identify as your input, what you identify as your input size, and how you write your algorithm too. I'm going to go ahead and write it like this. For I running from 1 up to n, or another way of writing it, let me go ahead and write it over here more pseudocodey, for each vertex V, right? Or yeah, let's go with X, because we're going to go X to Y. For each vertex Y, right? So there are n vertices here, n vertices here. If X in Y's list, Y, you could say Y dot list, or Y in X dot list, and then what I'm going to do is I'm going to negate this entire thing, then output false, because that edge is missing. There. Otherwise you output true. It looks almost the same here, except for it's a little bit different pseudocode wise. Output true. All right. Now again, it all depends on that 5-step process. What's my input? Well, the adjacency lists. Right. What's my input size? Well, I'll say that there are n lists. right? N lists. I won't have any regard here for the size of the lists. So what's my elementary operation? Probably this list test, right? X is in this list. Now at this point, that becomes a big question because is this a linked list? If it's a linked list, then checking checking for this becomes an order n operation, right? This becomes an order n operation because there could be, however, it depends on how many elements you have on that list. You could have up to n minus 1 elements, especially if you're answering true at the end, right? So the elementary operation here is, say, checking if an element is in a list. And by making that statement there, I'm saying that this operation right here is costing me 1, right? That's my elementary operation. So I'm not going to have a regard here for whether or not this is a linked list, which is going to be order n for linear search, or maybe it's a sorted array, in which case it'll be order log n for a binary search, or maybe this is a hash table, in which case it is amortized constant time, and so it's going to cost me 1, right? Okay. For it's going to be very, very similar here because I do this once, twice here. So if you want to be technical about it, you'd have 2 of those operations, but we had 2 of those operations over here anyway, but I treated this entire line as 1. But we'll go ahead and do it like this. I is equal to, or 1 up to n, and j is equal to 1 up to n because I blindly go for each vertex here. Right? And there are n vertices here, n vertices here. So this is just going to end up being like 2n squared. Right? Now, you probably don't need to do it like this. I could have written pseudocode instead that looked like this for each pair of vertices, x comma y, and now this analysis becomes n choose 2, right? Which is n times n minus 1 all over 2. That's how I got this one over here, because when you represent it as a matrix, then the upper diagonal, that's how many entries there are. So again, there were in fact, when I wrote up the key for this, I just put in 1 solution, and of course had in my key accept any valid solution, as long as your arguments follow logically from this. Okay, there are lots of different possible answers here, but if that's it, now I have to reconcile my choice here in part 2, that I said n lists. I'm treating one list as one thing rather than the size of the list, and so this becomes order n squared, right? Or theta n squared if you want, potentially. And unlike over here where we said, well, the list, the size of it is actually n squared, so if we run for n squared, it's actually linear. This is not linear. This is quadratic. Right? It's the same perspective. And this actually goes back to something we talked about in lecture or maybe on Piazza, that what is the input size of a graph? Really depends, right? Generally keep it simple. The number of vertices. Don't worry about the number of edges because you can't really get a good handle on that. It could be a sparse graph in which the edge set is only linear, has is order n with respect to the number of vertices. Or you could have a very dense graph where it's order n squared because it's almost a complete graph, but maybe not all the edges are there. So it really depends. Keep things simple and just say n, right? Because you know that they're polynomially related. If you change one and say that my input is like an adjacency matrix, then it has this behavior. If my input is an adjacency list, then it has this different behavior over here. And in fact, a list, if you replace that with a hash set or something like that, then it changes the details even further. Okay. Suppose you have an algorithm that takes a graph and 2 vertices and an integer less than or equal to the size of the vertex set, and outputs true if there's a path connecting x to y of length k. Further, suppose this algorithm runs in order time t. Use this algorithm to solve the Hamiltonian path problem. Give good pseudocode and analyze your algorithm. Right? So this should be pretty straightforward. I think you had to do this for your homework this year instead. But here's my input. My input is simply a graph, G, because now I'm not solving this problem up here that's solved for me by the algorithm A. I'm trying to solve the Hamiltonian path problem, not the given a graph, 2 vertices, and a K, output true or false. I'm given just a graph G, and I want to output true if G has a ham path, false otherwise. Okay. All I need to do is run that algorithm once. A Hamiltonian path, if the graph has 5 vertices, a Hamiltonian path would necessarily have 1, 2, 3, 4 edges. So in general, if a graph has n vertices, the Hamiltonian path necessarily is of length n minus 1. So all I need to do is get the result. Result R of that algorithm, A sub G x, y, and I've already done this in Sharpie, so I've done it. I've cut myself into a corner here, right? That's a result of one particular x and y. So let me go ahead and do that. We need to determine if there is a Hamiltonian path at all, not just particular between x and y, but for any x, y. And so I need to go into a for loop here. For each, and I'll use the trick that I was talking about before, for each pair of vertices, x and y, and I don't have to say each a pair of vertices because I can use math here to describe this as being in the vertex set. I'll ask, is there a Hamiltonian path there? If A on G and X and Y and N minus 1 and evaluates to true, remember it outputs true or false depending on whether or not there is a path of length K, then I will output, I'll stop and I'll output immediately, yes, true. Right. In particular, from X to Y, there is a Hamiltonian path because there's a path of length n minus 1. There. That's it. And then output false. Because for no pair does there exist a path of length n minus 1, therefore no Hamiltonian path. Now, again, the analysis here is one. It's going to be the graph here, and I will take the abstract notion of it's just a graph, period. There are n vertices, so my input is G, my input size is n, the number of vertices in G. My elementary operation here is invoking a call to that algorithm A. By the way, that algorithm exists, right? You programmed it. In fact, you implemented it in your first homework, but it doesn't necessarily run in polynomial time. Thankfully, though, we're given the condition here that it runs in order time t, right? So how many times is this elementary operation executed with respect to the input size? Well, how many pairs are there? N choose 2 times t sub n. Right? Now you know that the implementation that you ran, that you had, will, in the worst case, run in exponential time. So this will be some polynomial times an exponential, but we're going to keep it abstract. Suppose that we've solved the p versus np problem and somehow miraculously shown that it's that they're equal, and so this is some polynomial instead, right? It doesn't matter, but this is going to be n squared times t sub n. Right? I'm just keeping it abstract here. Okay. That's the idea there. Any other questions, or no? These are all live stream. Sound not working. Okay. All right. Now it's just plug and chug questions, meaning that here are some keys. Put them into a heap. Let's see, is this a min heap? So put these into a heap, an initially empty min heap, and I will change to just a pen here, since you can clearly see the keys there. In fact, I'll go ahead and zoom in a little bit more, right? Insert them into an initially empty min heap. Show any swaps that occur after insertion. So at the very top here, we'll go ahead and have 9, right? I put 9 into an initially empty min heap. 5, remember with a heap, you always insert initially as at the next available spot, right? Now 5 and 9, that is not a min heap because the minimum is not at the top. So we end up swapping, and we end up with 5 and 9 down there. Okay. All right, we insert 1. The next available spot is right here. 1. It violates the heap property because it is not greater than its parent, or it's with respect to the parent, it's has a child that's less, and so we swap those. And I forget, are we count up the number of swaps required? So 1, 1. There's 2, right? And we're left with 1 at the top, 9 and 5. Right? Remember, this is a min heap. This is not a binary search tree. It is a binary tree, but not a binary search tree. All right. Next one that we insert is 3. 3. And that's at the next available spot here. It violates the heap property with its parent, so we do a swap here. And that's our third swap. And we end up with 1, 9, 5, and, oops, sorry. I forgot to swap, and then 9 down here. Right. Good. The next one is 2. The next available spot is right here, is the right child of 3. We end up swapping, and that's our fourth swap. And so we're left with 1, 2, 5, 9, and 3 got shifted down, demoted. Okay. 4 swaps so far. 7 becomes the new left child of 5, and we observe that that does not violate the min heap property, so there are no swaps on this one. Okay. The next one we insert is 6, and again, no swaps. Right? So let me go ahead and rewrite it. 1, 2, 5, 9, 3, 7, 6. Okay? We've still only made 4 swaps. 4 is the next available one, or next one to be inserted. It violates with its parent, so there's our 5th swap. Right? And we are now have 1, and I hate rewriting these. That's why I would diagram them out and then take a snapshot or something. And especially since I screw up and not write it. So there we go. Remember, it doesn't go up any further. It could go up further if we had inserted 0 instead. That would have gone all the way to the top. So 1, 2, 3 swaps. In this case, however, there is only 1 swap because it's going to be greater than 2 here. Okay. 8 is the next one, resulting in no swaps because its parent is already less than it. So a total of 5 swaps. And this is the resulting min heap at the end. Okay. Same exact key sequence. Oh, I thought min heap. Okay. 2-3 tree, and then ultimately we do an AVL tree. So let's go ahead and do the 2-3 tree first. There we go. So into an initially empty 2-3 tree, we start with 9. That is a 2 node. Then we insert 5, making it into a 3 node. It has now 2 keys. Then we insert 1. 1, 5, and 9. It is now over full. You cannot have 3 keys in a 2-3 tree. So we end up promoting the middle element. It goes up, making this into the following tree. Right? Those are now, and I was drawing it with a, we can draw 2 nodes with a regular circle and 3 nodes with squares. It doesn't matter as long as it's clear. All right. Remember, we always insert into a leaf. So if we're going to insert 3, we come in, it's less than 5, we come down here, and that's a leaf. And so we end up making this into a 3 node. 5, 1, 3 has become a 3 node, and 9 is there still. The next one is 2. So what happens is 2 comes in here, it's less than 5, and it gets inserted over here, but it's over full. I'm showing this in stages here. And so 2 gets promoted up, splitting this 3 node into 2 nodes. Because when we promote a 2 up here, now we have 2 keys in the parent, and so we necessarily have to have 3 children. The way that we have that is by splitting up 1, 3, and 9. Okay. 2, then 7 is next. So 7 comes in. It is greater, but this 2 node, it can accommodate it by becoming a 3 node. So 2, 5, 7, 9. 3 and 1 are unchanged. They're still 2 nodes. You always insert into a leaf. 6 is greater, so we come down as is greater than 5, and so we need to insert over here. When we do that, this becomes over full, and so 7 gets promoted up. And so intermediate here, 2, 5, and 7. Right? And now we've got 1, 3, 6, and 9 as children. But we can't have 4 children, nor can we have 3 keys. So the next step is to promote 5 up, creating a brand new root. 2, 7, and then the 4 children here end up as 1, 3, 6, and 9. Okay. What was that we just inserted? 6 or 7? 6. All right. So 4, less than 5, greater than 2, and we always insert into a leaf. So that becomes 5, 2, 7. This one, it receives it over here. So 3 and, what was it, 4? That becomes a 3 node. And you can draw the others if you want. But otherwise, what I'm going to do, I'll go ahead and draw this. And the resulting 6, when I finally insert 8 at the end here, it's going to be greater than 5, greater than 6, and then that last node there can accommodate it, so it becomes an 8, 9, and that's a 3 node. But of course, you could show that into 2 stages if you wanted. Okay. Same exact sequence, but into an AVL tree. Yeah. There we go. Too much ghosting on the back. So again, we need to show the resulting tree configuration after each insert. We're also going to have to show the rotations. Okay. So nothing interesting happens until we've actually inserted 5, 9, then 5 gets inserted, and then 1 gets inserted. But let's go ahead and look at the balance factors here. This is 0. The balance factor of this one is 0 minus -1, -1 for a tree. So this is 1, which is still fine, right? Remember, in an AVL tree, you can have 0, 1, or +1. This one has a height on its left subtree of 1 minus -1, so that ends up being 2. This is unbalanced. It's positive, so it's unbalanced to the left. Looking at its child is unbalanced to the left. And so we end up doing a right rotation, giving us 5, 9, and 1. Okay. We insert 3, less than 5, greater than 1. We're not going to end up doing any rotations here. We can go ahead and indicate the balance factors if we really want to, but otherwise 2 gets inserted. I'll do it after we've inserted 2 here. 5, 2 is greater than 1, 2 is less than 3, so there. Okay. Balance factors of all of your leaves are going to be 0. Balance factor here is just like it was over here, 1, which is fine. The balance factor here, though, is -1 because it's empty left subtree, -1, so this ends up being -2. The balance factor here is bad, but it's unimportant because we're going to fix it around here. Right? So what kind of it's unbalanced, and it's unbalanced to the right because it's negative. We look at the right child; it's unbalanced to the left because it's positive, and so we end up doing a right, then a left, right, left rotation. And when I do that, I have 5, 9. 2 comes up to be the new root. 1 and 3. Balance factors of 0, 0, 0, 0. And this balance factor is going to be 1 minus 0. So it's unchanged from what it was over here because we fixed the unbalancedness, if that's a word, in the left subtree. So this ends up being not balanced. Again, if we didn't have that property, then we couldn't exploit that. If local changes caused imbalance all over the tree, then we would basically have to redo the entire tree, kind of like a rehash of a hash function of a hash table that gets full. Right? We just inserted 2, so the next one is 7, greater than 5, less than 9, and we can accommodate it over here. And you can see that that's not going to change any. It's going to change balance factors, but none of them are going to be unbalanced. 6, greater than 5, less than 9, less than 7, so it gets over here. Hopefully you see immediately that that's a right rotation, right? Because it's 0. It's exactly like over here, 1 and 2. And so we do a right rotation, and we're left with 5, 2, 9. Oops, 7 comes up to become the new root. 9 goes down, and 6 comes up. 1 and 3 are unchanged here because we're only making local changes. All right. So this is a right rotation, right left rotation here. We end up inserting what we just did was 6. So 4 is next. Less, greater. Now, I'm not going to write the balance factors here, but before, all the balance factors ended up being 0. Let's just write these balance factors here. 0. This one is going to end up being -1 minus 0, so it changes its parent's balance factor. Its parent or grandparent here, with respect to 4, is going to end up being 0 minus 1, so -1. And of course, this is going to end up being 1, 2 minus 1, so it's going to be 1. Right? It's unbalanced to the left, but only slightly and tolerably so. Right, we do have to update the balance factors going up. The rest of them are still 0, though. Right. I did write all the balance factors. Right. I wasn't going to do that, but I wanted to draw your attention to the fact here that we started with a full tree here. So no matter what, just inserting one more thing is not going to end up with any rotations because there's nowhere else for it to go. If we rotate anything up to get 4 up shallower, that necessarily pushes something else down. Okay. Likewise, when we put an 8 here, greater, 8, there's nothing else that you can do to until you make one side unbalanced more than the other side. We're just filling this row right here, this level. But the balance factor here are now changed. 0 minus -1, so this becomes 1. The balance factor here is going to be 0 minus 1, so -1. And then the balance factor up here then becomes, let's see, 1, 2, 1, 2. So it gets updated to 0, right? We actually made the root more balanced by putting that over there. Okay. That's an AVL tree, and we are now done with. Oh no, sorry, there's one more. Right? I don't think I put this on this year's midterm, but or any hashing on this year's midterm, but we can get some practice here. We'll just do it right here. All right, same exact keys. Put them into a hash table of size 13, and there's our hash function to do it. So I'll write the hash table as we go along here. 9 times 3, or 3 times 9 plus 5 mod 13, and this is our hash function for 9, right? And that's why I've got Wolfram Alpha up here to do my work for me. 3 times 9 plus 5 mod 13, 6. 0, 1, 2, 3, 4, 5, 6. So 9 gets hashed to this cell right here. Right. The next one is going to be h sub 5. And I'm just going to go ahead and use Wolfram Alpha for the rest of these. That's 7. So 5 gets inserted there. By the way, we have to count the collisions and use linear probing to resolve the collisions. So we have not hit any collisions yet. So, but I'll have a collision count over here, 0 so far. The next one that we've got is 1. I could do that in my head. 8. There we go. The next one is 3. That's also 1. That goes to 1. Oh. No, that's right. It went 1 went to 8. 3 goes to 1. There we go. Still no collisions. 2. That's going to be an 11. So 9, 10, 11, 12, 13. Oh, nope. It's of size 13. So the index will go up to from 0 to 12 here. So 11, what was it? 2. There we go. Still no collisions. The next one is 7, and that goes to 0. 6, maybe this is large enough that there were no collisions, goes to 10. And 4 goes to 4. Boring. 8 goes to 3. So trick question, if you want to call it a trick question. It was large enough that there were no collisions. Right? Great. That's not that surprising, since you might have seen the pattern, or I implied the pattern in lecture, that if you when you write a hash function, it's good to choose primes as your multipliers and of course as your mods, because if you, for example, if they were not relatively prime, then you could have a hash function that trivially only mapped everything to at most half of the cells or something like that. That you could get into a cycle where nothing would ever map to, say, I don't know, an even integer, and so you'd be effectively wasting half of your space. In general, choosing primes can solve that problem, and so that's why I've got 3, 5, and 13. Right? It's just once you know that, it's your natural inclination to choose those things. Right? Okay. All right. Any questions? Again, we're on a 10-second delay here, so. Let me go ahead and check really quick here. 2 unread posts. Okay, nope. Okay. Well then, again, the midterm was to recap what we might have missed because of the audio at the beginning. To recap, the midterm, your actual midterm, was released late last night. Post on Piazza was made about it. You have until midnight tonight, that is Tuesday, July 28th, 1 minute before midnight, to submit that to Canvas. It does have to be PDF, just like all of your assignments. You can go ahead and write down things, with your handwritten answers, as long as you're using one of the apps that we recommended to take snapshots of it and produce a PDF of it. If you want to write it up in LaTeX, great, go ahead. If you want to make all of your figures in LaTeX, that's also fine, if you know what you're doing. But otherwise, good luck on your midterm. It is open book, open note, open computer, of course, but it is closed partner. So don't work with anybody else in the class or outside of the class on your solutions. Okay. Homework and midterm are due tonight, so make sure that you've got you give yourself enough time if you have